Welcome to a lesson with Dr. Powell. Let's talk about big O notation and the notation which looks like less than less than. These two notations can give us the same basic idea, which is given two functions, let's suppose like n squared and n cubed, or maybe even let's do 1 over 10 n cubed. Now, at first, if you were to graph these two things, n squared, thinking of n as being like on the x, as being x, and 1/10 n cubed. Now, at first, 1/10 n cubed is going to be smaller, but eventually, there's going to be some kind of crossing, and n cubed is going to be bigger. Why is that? Well, anything with an n cubed eventually trumps this. You could even think of it in terms of a fraction. 1 over 10 n cubed over n squared for a large enough n. This is the top is going to be bigger than the bottom. In fact, you can see exactly what that is just by doing a little algebra. So this is equal to n over 10. So when n is bigger than 10, notice that this fraction will be bigger than 1. Well, that means that this will eventually be bigger than that. In particular, we say that if you have two functions, f of x and g of x, such that if there's a point n, such that if x is past that point, then f of x will always be less than a multiple of g of x, multiple k, so just some multiple. It doesn't even have to be less than g of x itself, just some multiple of g of x. Then we can use this notation. This is kind of like an asymptotic less than. F of x is asymptotically less than g of x. Or another notation for that is this big O notation, which is f of x is the big O of g of x. So in this particular case, we actually have that n squared is the big O, and big O actually here means order. So n squared is less than the order of, or is on the order of n cubed, being in particular less than the order of 10 cubed. So we could just eliminate the constant 1/10, because really constants are eaten up into this notation as well as this notation. And we can just say big O of n cubed. It's always less than it. In particular, you could even say this. You could say n squared is equal to the big O of 1/10 n squared. I mean, eventually 1/10 n squared is always, well, it's always less than n squared. However, a multiple of it will be larger than n squared. I mean, multiply this by 20, for instance, that'd be 2n squared. Well, of course, that's going to be bigger than n squared. So really, this big O notation, you can kind of eliminate constants completely. Let's think about this a little bit. What if we had something like n squared plus n cubed plus 3? Now, eventually, n cubed is bigger than n squared. Eventually, n cubed is bigger than 3. And eventually, for large enough n, you could say, well, 3 times n cubed is bigger than all this. Well, but constants don't matter really in big O notation. So you can just say this is on the order of n cubed. You just kind of take the largest guy, and that really tells you what the big O is, or you could equivalently write less than, or asymptotically less than n cubed. And that would be appropriate. You could have log n plus n. This is going to be less than, asymptotic less than n, or equal to the big O of n, since n is bigger than log n. I mean, even if we had 5n plus log of n, that would still be, so when we have this situation, this will again be equal to the big O of n, or asymptotically less than n as well, even when we have a constant in here other than n. I mean, we can kind of just loosely think of things as being without their constants, and then just pick the larger of the things if you're adding. If you're multiplying, it should be pretty clear, like n log n times, like 2 to the n or whatever. This is just what it is. Big O of, the things just multiply together inside. So if you have something that's the big O of 2n, something that's the big O of n, something that's the big O of log n, they're just going to multiply together to be the big O of 2n and log n. So in particular, if you had something like 2n plus n times 1 plus n times something that's 1 plus log n, then since this right here, the big O of this is 2n, the big O of that's n, the big O of that is log n, then the big O of all of this is just that. So they just kind of naturally multiply together in multiplication. In addition, you just kind of take the bigger one. And using that idea, you can easily and quickly work with this big O notation just in practice. And that is big O notation and asymptotically less than notation. Thanks for watching.